Hello everybody. Today's lecture on square wave permanent magnet brushless DC motors. On the previous session, we discussed about that normal DC motor and also the brushless DC motor. PMD, permanent magnet brushless DC motor. We have different types of motors. Here, here, if you come across this square wave permanent magnet brushless DC motors, nothing but we are having different types of square wave and also sine wave. That is, actually, if you go for a DC motor, if you go for observe that the DC motor is the EMF generation waveform is to be different within the motor. Why? Because it is actually the EMF is generation is possible within the motor also. That is a counter EMF. If you come across this counter EMF, the counter EMF waveform is also different. Here, with respect to that, we are having that permanent magnet brushless DC motors, BLDC motors have two types. With respect to waveform, that is a square wave and also the sine wave. Square wave with 180 degrees and also sine wave with 180 degrees. We're having different types of motors. These two are important. Nowadays, applications, we are using that electrical transportation of two-wheelers and also four-wheelers also. Here, if you come across these two-wheelers, we are using the permanent magnet brushless DC motors of 250 watts range, 350 watts range. With respect to that, for 250 watts and also the 350 wattage ranges here, the PMDC motors have having commutation. Why? Because the commutation is very much important. Normally, if you come across this normal commutation, that is different. That is a mechanical commutator. We are calling it as a mechanical commutator. Now here, we are using that the electronic commutator. Electronic commutator using the power semiconductor switches. How the electronic commutator works, and also what are the comparison between the electronic commutator and also the mechanical commutator, we will observe now. First of all, this is the electronic commutator. We actually know that mechanical commutator, the same armature winding is to be connected towards the commutator segments. Okay, each segment has to be placed into form a circle. That is nothing but a mechanical commutator. On that mechanical commutator, we placing that brushes, the carbon brushes or the copper brushes. Here, in the same way, we are replacing the commutator segments into using a switches, with using of a switches. That is power semiconductor switches. Here, if you observe this diagram, we are having totally 12 tappings. Nothing but if you consider on the mechanical commutator, it is having that 12 segments. Okay, here we are giving that 12 tappings on the armature winding. This is the armature winding, and the internal part is to be a permanent magnet. It is the permanent magnet shown. Okay, and outside is the armature winding. Okay, here with respect to that armature winding, the armature winding is to be connected towards the tappings. Here 12 tappings we are provided, totally 12 tappings. On the next diagram, if you observe, I am not shown with 12, but it should be more number. Okay, if you observe, that is having that more number. Don't worry about that. Why? Because I shown like that. Why? Because the switching diagram is to be like that. Actually, this is the single line diagram for that using an armature winding. Here, we are not shown with armature winding, but on that tappings, we have been shown with the switches. These are nothing but the semiconductor switches. If you observe, this is the semiconductor switches. Okay, here on that particular semiconductor switches, by giving the signals towards the switches, like nothing but at what at this instant, uh, at this instant, which switch can be turned on, number which number of the switch can be turned on. That is, if you consider 12 number of switches, 12 number of switches we are having totally 1 to 12. Here each switch can be, if you come across this, one switch and also another switch has to be attached. If you come across this one first switch and the seventh switch, first switch and also seventh switch. Why? Because the current is to be moving in a circular path, in a circuit. If you consider in a circuit, this 1 7 is a 1 7 switches are making it to form a switch circuit. Therefore, with respect to this, the current is entering into the first tapping and leaving into the seventh tapping. Current is entering into the first tapping and leaving towards the seventh tapping. Okay. On the next time, if you consider 10th tapping and also the fourth one, there is a combination. Nothing but if you come across this, with respect to the combination only, the circuit can be formed. With respect to the combination only, the circuit can be formed. Therefore, whenever there is forming of a circuit, therefore, while providing the tapping onto that particular switch, by connecting the switch towards the tapping, therefore, with respect to that particular tappings only, the current will be moving. Why? Because without any closed path, closed circuit, there is no current. Okay, like that, the tapping of the first one and also seventh one, it should be forms a circuit. Here, if you observe, S1, S2 to S12 and negative of the supply at node Y, we consider here through switches S1, S2 and S12. Here I am not shown with the diagram, but it should be different. But having the 12 tappings, 12 tappings having with respect to 12 switches. Here we are placing the switches. I am not shown here, but if you observe the next diagram, these are the switches, but having more number of switches. Okay, totally 12 number of switches we are placed. With respect to the 12 number of switches and also the 12 tappings, here the supply is given towards the armature winding. Next one, how about the switching process? Switching process, this is very important. Here, if we come across the switching process, each and every tapping will be continued. If you come across this S1 and S1 dash, S1 and S1 dash, S1, S1 dash. At the same time, the current is to be entering into the circuit and leaving towards the circuit of S7 tapping of the S7, tapping through S7 switch. And also here also S10 and S4, like that. This is nothing but the switching process. And next one, this is actually some single line diagram with respect to the switches. If you come across this, when will the positive and when will the negative supply can be applied towards the armature windings? Here, if you come across this positive and also the negative supply of a DC supply which we applied here is S1 and S2 up to S12. Again, S1 to S12 dash has been taken. Why? Because if the motor can be operated in reverse direction, and also if you can, the motor can be operated in forward direction. Two directions can be either of the direction can be operated by the motor. Okay. Therefore, by giving this interchanging the polarity of the supply with respect to the switches, therefore there is a possible to operate the forward direction or either in a reverse direction of the motor. Here, if you come across this S1, suppose S1 is to be switched on. S1 is to be switched on. S1 makes the positive and that S1 is to be switched and the supply current is to be moving like this towards the armature winding. Okay, when will it should be return path? Return path here it should be moving, that is S7. Nothing but either for every time, for each time, two switches can be turned on. Two switches. Why? Because one is entering and also one is leaving. And next one, if you come across this, when switch S1 and S1 dash are closed, the others are in the open position. Therefore, the DC supply is given towards the tappings 1 to 7. There are two armature parallel paths. We have actually armature parallel paths or two parallel paths. With respect to the parallel paths only, the current is to be moving towards the armature winding. Okay. Next, that is the parallel path. If you observe, this is the parallel path. Here, the parallel paths are 1, 2, 1 to 7. 1, 2, 3, 4, 5, 6, 7. This is one of the parallel path. Next one, second one is to be 1 to 12, 12 to 11, 10, 9, 8, 7, like that. These are observed on the armature winding. This is the nothing but with respect to the parallel paths only, the current is should be moving. The armature winding is getting excited. Okay. Here, they set up armature MMF along the axis towards the 7 to 1 or 1 to 7. Magnetomotive force within the air gap can be produced with respect to when 1 and 7 are switched on. Okay. After a small interval, S1 and S1 dash are kept open and S2 and S2 dash are closed. Okay. After nothing but if you observe, this is the S1 when S1 and S1 dash are closed. Therefore, 1 to 7 tappings are turned on through the switches. Therefore, this is one parallel path 1 to 7, 1, 2, 3, 4, 5, 6, 7. This is one of the parallel path. Next one S10 and S4. Okay, like that. After a small interval, S1 and S1 dash are kept open and S2 and S2 dash are closed. The DC current passes from tapping 2 to 8, sets up MMF in the direction 8 to 2. Okay, if you observe, these are the important points for the procedure how the electronic commutator can be worked. After a small interval, S1 and S1 dash, S1, S1 dash can be opened. Why? Because whenever these two are open, switches are open, then only the second switch, S2 and S2 dash are closed. There is a possibility. Okay, so that's why first you have to open the switches S1 and S1 dash, and next one S2 and S2 dash are to be closed. Okay, next one, then DC current passes from tapping 2 to 8, then set up an EMF in the direction 8 to 2. Okay, next, thus by operating the switches in a sequential manner, it is possible to get a revolving MMF in the air gap. Why? Because within the air gap, whenever there is an MMF, magnetomotive force or magnetic field within the air gap, then only possible to produce the torque to operate the particular load. So, by operating the switches in a sequential manner, in a sequence of operation is important for the switches S1 to S7, S10 to S4, again S1 to S7, like that. Therefore, what should happen? The switches S1 to S12 and S1 dash to S12 dash can be replaced by power electronic switching devices such as SCRs or MOSFETs or IGBTs. Therefore, there is a possibility to control over that switches. We are getting that controlling. Okay, normally if you use any normal, we are having different types of semiconductor switches, either uncontrolled switches and also the controlled switches. If you go for an uncontrolled switches, whenever there is a availability of the supply be across the switch, therefore there is a possibility to turn on that particular switch or switch on the switch, turn on the switch. Then if you go for in place of uncontrolled, go for the controlled. So that's why given that power electronic switching devices such as SCRs, MOSFETs and IGBTs. Nowadays IGBTs are using insulated gate bipolar transistors and also the MOSFETs, metal oxide semiconductor field effect transistors. These two switches are using. Why? Because which is having a controlled nature. With respect to controlling the gate, then only there is a possibility to operate that particular turn on and turn off processor in a sequential manner. Okay, whenever the operation is to be in a sequential manner, therefore there is a possibility to getting that MMF or within the air gap a magnetic field is possibility. Then there is a possibility to torque production. That is by replacing the normal semiconductor switches with a using of a controlled switches of SCRs, MOSFETs or IGBTs, or even go for a power transistors. Next, when SCRs are used, suitable accommodating circuit should be included here. Okay, then there is an we have that most advantage is to be while we are going for the uncontrolled switch, sorry, controlled switch in place of uncontrolled, we are getting that better option is to be sequential operation is to be operated in a stable manner. Nothing but a stable manner means you should be first you have to operate 1 and 1 dash, next to 2 2 dash, next to 3 3 dash. That is a sequence of operation. But if you come across this, there is a requirement of the commutation towards the circuits. So SC devices, either you are using SCRs or either you are using MOSFETs, IGBTs, or even using the power transistors of a bipolar junction transistor, field effector transistor. Okay, of a power transistors which we are using, if you use a commutating circuit here without a commutation, the sequence of without a commutation, the sequence of operation is also not possible. The sequence of operation is also getting problem. Therefore, combination circuit is to be required here. Combination circuit is to be needed for the power switches of SCRs, or either you are using MOSFETs, IGBTs, or power transistors. Depend upon the type of the switch you have used or the type of the system you are operating. Therefore, there itself depend upon the commutating circuit. That is, even you are using line commutation, natural commutation, or forced commutation. Forcibly you are off turning off the switch. Line commutation or the natural commutation, or it should be whenever the supply is to be cut off. Therefore, there is a possibility to turn off that particular thyristor or switch. Okay. Therefore, depending upon the type of the forced commutator employed, each switch requires on or off, on or two SCRs and other commutating devices. As number of devices is increased, the circuit becomes very most probably it should be difficult. Remember, some means it should be operation should be becomes efficiency should becomes less when will you increase the more switches. And suppose, and this is the commutation circuit. If you come across, this is the commutation circuit. Here, commutation circuit provided with a IGBT switch or SCR it should be, and across in parallel with a diode has been placed. That is used as a freewheeling diode. Therefore, 6 thyristors or the 6 switches are used here. Across the 6 thyristors or the 6 switches, uncontrolled diodes were used. These are used for the freewheeling purpose. Whenever there is an inductance, nothing but within the armature winding, we are having some inductance value. Okay, even, but here amount of energy that is to be available in the inductance value within the winding, that it should be getting fed back towards the circuit supply. That is the purpose of using this commutation circuit across nothing but in parallel with the diode with a switch. Okay, IGBT switch across where we are placing the diode. That is the purpose. 6 thyristor switches were used here. In each SCR, where in parallel with the diode is also placed. And also this is a 3-phase BLDC motor. Okay, this is the star connected armature winding. Next, how the delta connected armature winding should be. How the delta connected armature winding. Here we shown that in previous it is a star connected armature winding. How, if we come across this, delta connected armature winding is also there. So with respect to the delta connected armature winding, for normal electronic commutator, usually 6 switching devices are employed. Actually, for normal electronic commutator, if you go for further limit, we are using now 12 electronic 12 switches. But for normal electronic commutators, usually 6 switching devices are employed. Then the winding should have 3 tappings. Okay, 6 means it should be 3 tappings. 12 means it should be 6 actually. Okay, but some of the conditions we consider only 4 also. Therefore, the winding can be connected either in star or in delta. Either of the connection is to be used. either it is in a delta connected or in a star connected the armature winding, you have to connect directly towards the power circuit, switching circuit. And this is the delta connected RYB phase. Here, this is the delta connection if you observe, and each phase is to be connected with respect to in between two SCR switches. Okay, two SCR switches. Next one, if we come across the star connected armature winding, there is a replacement of the end-to-end connection towards the phases has been replaced with a single connection. That is, from all the switches in between the two switches, we are tapping the connection for the each phase of the armature winding. Therefore, we are getting that three-phase winding of a BLDC motor, and this is the rotor, and also rotor positioning sensor. This is RPS is nothing but the positioning sensor with respect to whenever the supply is given towards the across the circuit. Therefore, whenever the thyristor T1 and T2 will be turned on. Suppose if the switch is to be turned on, therefore this is the path, and we are making into neutral connection. There is a neutral connection also. Therefore, with respect to the star connection, we are getting the supply towards the armature winding. Therefore, with respect to armature winding, getting the supply here an MMF should be getting developed within the magnetic air gap of the armature and also the field. Therefore, thereby the torque can be produced. This is the type of the connections for the armature winding in a delta and also the star connection. Next one, comparison between the mechanical commutator and also the electronic commutator. If we come across this mechanical commutator and electronic commutator, you know that a mechanical commutator having that segments. We observe that one by one point. Here, commutator is made up of a copper segment. Commutator is made up of a copper segment, and commutator is made up of copper segment and mica insulation. Brushes are carbon or graphite. Okay. Next one, power electronic switching devices is used in the commutator. It requires a position sensor. In place of the commutator segments, in place of, we are using normally commutator segments, and each commutator segment has been given with a mica insulation. Why? Because if you place first commutator segment and you have to attaching the next commutator segment, there is a direct contact in between the two segments. There is no direct contact. How don't provide the direct contact? Why? Because there is a short circuit can be getting. There is a possibility. Therefore, collection of the current by the brushes is problem is to be getting sparks, more amount of sparks. Okay. Why? Because when the load on the motor is increased, therefore requirement of the current by the motor can be drawn by the motor is from the supplies increases with respect to the load. Therefore, must and should be provided with respect to in between a commutator segments. We have to provide a mica insulation. Okay, and the brushes are of the carbon or even a graphite brushes. Next, in place of the mica commutator segments of a copper, we are replacing with a switches. That is the power electronic switching devices which are used for the commutator, and also it requires a compulsory rotor positioning sensor. A sensor must and should be required. Okay, by the rotor. Next one, commutator arrangements are located in the rotor. Actually, this is the, if you observe, this is the commutator arrangements are located in the rotor, and it is located in the stator. There is a huge difference between. Here the commutator is placed in the rotor, nothing but the armature winding. Here it is located in the stator itself. Okay, nothing but commutator. Rotor means here on the shaft. Here it is located on the stator of the armature winding. Either it is a delta connected armature winding or in a star connected armature winding. Next one, shaft position sensing is inherent in the arrangement. Shaft position sensing is inherent in the arrangement. Next one, separate rotor position sensor is required here. Number of commutator segments are very high. Normally, the commutator segments are increases with respect to the capacity of the motor is increasing. Next one, on the electronic switch commutator, number of switching devices is limited to 6 only. Up to 6. We used that you go for 3 or 4, sorry, 2 or 4 or 6. Therefore, number of switching devices is limited to 6. Most of the BLDC motors that are operating with using of these switches is to be 6 only. 6 only. Now, in two-wheelers also we are using the brushless DC motors. With respect to this brushless DC motor, number of switching devices is limited to 6 only. Okay. Next one, those are highly mechanical commutator are highly reliable. But what about the electronic commutator? Electronic commutator reliability is improved by specially designing the devices and protective circuits. And nothing but a controller is must and should be the main heart towards the BLDC motors. The controller. Within the controller, therefore, we are using the switching devices. Therefore, the switching devices are operating in a proper manner or in sequence operation. Therefore, reliability is improved. Okay, by using this specially designing the devices and protective circuits. Next one, difficult to control the voltage available across the tappings. Difficult to control the voltage available across the tappings on the mechanical commutator. And if you come across this electronic commutator, the voltage available across the armature tappings can be controlled by employing pulse width modulation techniques. So we have different types of techniques. There is the pulse width modulation, sinusoidal pulse width modulation techniques, and also we are having that different types of modulation techniques: square wave modulation, sine wave modulation, okay, and also sawtooth wave modulation technique. We have different types of modulation techniques with respect to different modulation techniques only where the voltage amount of the voltage that it should be giving towards the motor using the commutator, there is a possibility. So the voltage available across the armature tappings can be controlled by employing pulse width modulation techniques. Next one, interpolar windings are employed to have sparkless commutation within the mechanical commutator. Next, if we come across this electronic commutator, by suitable operating the switching devices, better performance can be achieved. Okay, nothing but suitable operating the switching devices means if you use a 24 volts BLDC motor with a 250 watts capacity, then you have to select the proper IGBT switch or switching device. You have to select a proper device. With using of this proper device only, there is a possibility of improving the efficiency and also improving the sequence performance of that motor. These all the values are improved. Okay, so these are the comparison between the mechanical commutator and the electronic commutator points. Next, if you come across this BH loop, why we are discussing about this BH loop means here we are using that permanent magnet. We are using the permanent magnet. Here, with respect to the permanent magnet, if you use here the permanent magnet, if you come across the permanent magnet, what type of a magnet, permanent magnet you are using to produce the magnetic flux within the air gap to getting the torque, required torque by the motor. Therefore, what is the withstand capability for the temperatures? Temperature variations is also increasing. Nothing what we are having summer and also winter seasons. Therefore, copper winding depend upon the loaded conditions on the armature winding. The motor winding can be getting heated. That is, more temperatures can be increases on the summer seasons. Therefore, type of the material should be must and should be how to improve the quality. Therefore, the permanent magnet life can be improved. Nothing but life means here the flux density availability and also intensity of the flux value within the air gap. These all are improved. Whenever these all are having improved conditions of a permanent magnet, therefore there is a possibility of high torque values. And next one, the permanent magnet, we are having different types of permanent magnet materials, that is neodymium, iron, boron, and also if you go for lithium ion, sorry, not lithium ion, permanent magnet. Neodymium iron boron has the highest energy product of all commercially available magnets at room temperature. It has a higher eminence and also coercivity in the motor frame size for the same output compared with the motors using ferrite magnets. We are having different types of magnets. Those are nothing but soft magnets, hard magnets, and also comes under this hard magnets, ferrite magnets. Ferrite magnets comes under the category of hard magnet. Therefore, uh, those are those are having the capability to produce the magnetic flux on that range. Even the temperature values are increases. Okay, so uh, so we go for ferrite magnets. If the ferrite magnets are using those, the economical point of view, those are high cost. So, but both of the above stated magnets are sensitive to temperature and care should be taken for working temperature above 100 degrees Celsius. When actually they have to withstand for up to 100 degrees Celsius, there is no problem. So, but even for the temperature value has been increased, there is a problem. For very high temperature applications, all nickel or rare earth metals of cobalt magnets must be used. Okay, for above 100 degrees Celsius, we go for that all nickel and also rare earth materials. And how the BH loop can be nothing but if you go for, if you are designing any permanent magnet, if you are taking any permanent magnet, considering any permanent magnet to design a motor or to manufacture any motor. Therefore, these type of materials, which type of materials are suitable for this temperature, more than temperatures, then we go for the choosing the materials of different types of alloy materials and making that permanent magnets. Next one, BH loop. If you observe, this is the BH loop. These are drawn for flux density and also intensity. Okay, and this is the remanence and also the coercivity. If you observe here, this is the remanence B suffix R on the BH y-axis. On the x-axis, we have the coercitivity. Here, if the width of this increases, the coercitivity value has been increases. Here, the x-axis shows that magnetizing force or field intensity, and y-axis the magnetic flux density. An unmagnetized sample has a flux density is equal to 0 and also intensity is equal to 0. Nothing but the graph shows is to be 0 point and unmagnetized. Okay, and when it is a magnetizer means therefore the curve should be increasing like this and moving up to A and up to B, and after that should be C and D. Again it should be coming towards the A and towards 0 like that from OAB. And then we observe that how the curves for different points we are giving that OABC. Here curve OA shows that if it is subjected to a magnetic field, magnetic fixture, an electromagnetic with shaped pole pieces to focus flux into the magnet. Then B and H in the magnet follow the curve OA as the external ampere. Then turns are increased. Here, external ampere turns are increased. Here, O to A. O to A has to be smallly increasing, developing the flux. Okay, the magnetic flux should be increasing like this. Okay, OA. If you observe OA up to this point. Okay, next one. If the external ampere turns are switched off, the magnetic relaxes along AB. AB along relax when the magnetic flux is to be nothing, when a supply is to be giving switched off. Therefore, there is some availability of the magnetic flux, but what is the curve? The curve should be shown here up to A to B, and it stops here. Okay, next one, the operating point of the field intensity in the magnetic flux depends on the shape of the magnet and also permanence of the surrounding magnetic circuit. If the magnet is surrounded by a highly permeable magnetic circuit, that is, if it is kept that its poles are effectively shorted together. So intensity is equals to 0, and then the flux density is the value at point remanence. Permanence means the maximum flux density that can be retained by the magnet at a specified temperature after being magnetized to up to saturation point. This is the permanence. What about the curve BC? External ampere turns applied in the opposite direction cause the magnet's operating point to follow the curve B through the second quadrant to C. Okay, up to C. Next one, curve CD. If the ampere turns are switched off at C, FC, the magnet relaxes along CD. It is now magnetized in the opposite direction, and the maximum flux density is it can retain when keep is at BR up to BR. This is the BR. Here, this is the point. To bring B to 0 from negative remanence point D, the field positive HC must be applied. Next one, the entire loop is usually symmetrical and be measured using instruments such as hysteresis graph. Okay, hysteresis graph. This is nothing but a BH loop or hysteresis loop. Soft permanent magnets. Soft permanent magnet materials have knee in the second quadrant, such as oligo materials. Oligo magnets have very high remanence and excellent mechanical and thermal properties, but they are limited in the demagnetizing field they can withstand. These soft permanent magnets are hard when compared with the lamination steels. The hysteresis loop of typical iron non-oriented electrical steel is very narrow when compared with oligo. Okay, we're having different types of rare earth materials and also the ferrite magnets and also oligo materials. We are using neodymium. We are used. Those are having that more advantages compared to this. Next one, if you come across this demagnetization curve, okay, demagnetization curve. This is the in the absence of externally applied ampere turn, the magnet's operating point is at the intersection of the demagnetization curve and the load line. Here, intersection point. Here, this is the intersection point. If you observe, okay, it is the intersection point. Nothing but when the ampere turns are switched on. Nothing but when the winding has been given towards. Suppose the permanent magnets are not. Actually, if you go for a normal winding means when you are giving supply and then it is excited. But here we are choosing the permanent magnets. Here, in the absence of external ampere turn, the magnet's operating point is at the intersection of the demagnetized curve and the load line. Up to this point only, the flux density should be okay. Nothing but whenever the magnetic field, sorry, whenever the armature winding is to be given the supply, whenever not given is here, absence of external ampere turn is this is operating point. If given means it should be operating point is increases. The slope of the load line is the product of mu naught and the permanency and the coefficient of the external circuit. Here, this complete relation shows that what type of the materials you have to use, what type of the material you have to choose for getting the for providing that better advantages. Nothing but providing that magnetic flux, that is high permittivity with a possibility. That is a permanence, high permanence value. Okay, less coercitivity force. Okay, those permanent magnet materials are chosen for the BLDC motors or even for a permanent magnet DC motors also. Therefore, by choosing these type of motors, we are getting better applications at any temperature. At any temperatures, even for a greater than 100 degrees Celsius of temperatures, also they can operate. And this is the today's class on permanent magnet materials and also different types of electronic and mechanical computers. And I hope understand all of you these topics today. Next, we will discuss about this principle of operation. Also, we directly go for the square wave permanent magnet brushless AC motors. Thank you.